Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Our speaker will be Andrew Mccray, presenting work done by Andrew and his faculty, mentor Zong Shao of Yale. I'd like to share this brief biographical statement with you. Zong Shao is professor of computer science at Yale University. His research interests include programming languages and compilers, proof-carrying code, language-based security, typed intermediate representations, and formal methods. He's a key developer of the standard ML of New Jersey, SMLNJ, compiler, and the architect of the higher-order typed intermediate representation named Flint, now used in the compiler. He currently leads the Yale Flint project to develop a principled compiler infrastructure and runtime for certified binaries. Zong received his PhD in computer science from Princeton in 1994. Andrew Mccray is a fifth-year graduate student at Yale University. His research interests include programming languages and compilers, typed intermediate languages, and machine-level Hoare logic. He worked for 2 summers at Cedilla Systems on Special J, a proof-carrying code compiler for Java. He received his Bachelor of Science degree in computer science from Carnegie Mellon University in 2001. And the talk here is Typed Compilation of Objects.
Okay, thank you. Right, so as it says, I'm Andrew, and I'm going to talk about typed compilation of objects. So first, a little bit of background. So modern object-oriented, runtime systems like Rotor are very big pieces of software. An error somewhere in the garbage collector or the JIT compiler can lead to a type safety problem. Like if we have an out-of-bounds array access or something like a pointer getting treated as an integer or vice versa. And as we've all seen in the news, a safety problem like this can in turn lead to a security problem. And given that you're supposed to be able to just download random things from a person on the internet that we don't necessarily trust, this can be bad. So what we would like to do is reduce the amount of code that we trust. Because the less we have to trust, then that means that's the less places that something can go wrong. So can we avoid trusting, for instance, a compiler? What about parts of the runtime like the type tests or the garbage collector? So I'm going to talk a little bit about trying to minimize the TCB, which is the part of the compiler we trust. So first, I'm going to talk a little bit about type compilation of objects, kind of in general. And then I'm going to discuss a sort of lightweight object typing system that we developed. And then I'm going to talk a little bit about dealing with object-oriented programming at the assembly level using Hoare logic. So first, here's our diagram with the standard kind of runtime that you'd imagine in CLR or something like that. So we have our untrusted input, which is a bytecode plus some types, and then we check that, and then compile it to some binary, which we combine with a runtime and then execute. So as you can see here, we don't trust the thing we download, but after that, it's all we can do whatever it wants, and errors at any stage inside the blue box can potentially cause problems. So what we want to do is reduce this. So the first step we can take is that the same thing is the approach taken by proof-carrying code and typed assembly language, where now our compiler doesn't just spit out a binary; it also spits out some kind of types. So it's kind of something that proves that the assembly code we have is still safe. So we have our input, which is has types and is type safe, and then we have our assembly output, which is also type safe. And then now we can check that, and then combine it with a runtime, and then execute it. So now we don't trust the compiler anymore, which is good because the compiler is very large. And now the safety of our entire system does not depend on the compiler being safe. But we still have to trust the runtime. Because usually in these systems, the type system we use for the binary is not really expressive enough for all the kinds of crazy things we need to do, in the garbage collector or whatnot. But it's still a step forward. So how do we actually produce these types? So we have an input that we know is type safe. We're not dealing with C or something. And so we want to take these high-level types and sort of lower them as we're compiling. As we're lowering the program, we want to lower the types at the same time. So we need a type system that can describe objects at the machine level. And we don't want to have to change the compiler a lot. As I said, compilers are really big. And if we add lots of machinery just for type checking, then every optimization phase has to deal with them, and it gets pretty messy. And if it requires a lot of work, then people are less likely to adopt it. And also, there's been a lot of previous work on low-level objects type systems, but a lot of it involves all sorts of hairy type theory, a lot of existential types and recursive types, and if you're dealing with a compiler, you should be able to think about the types at the same level of abstraction as you're thinking about the program. So, for instance, you want to think about things in terms of objects. The compiler thinks about objects and virtual method tables and methods, and we would like the type system to be able to reason about things at that level too. If you can understand the intermediate representation, you should be able to understand its type system without too much trouble. So to satisfy these two requirements, we want to produce what I call a lightweight type system. So, what properties do we want this lightweight type system to have? So the most important thing, above all, is that it must be sound. What does this mean? Well, if it passes the type check, if the type checker says this program's okay, then we want to know that this program will be memory safe. It won't crash. It won't treat pointers as integers or integers as pointers. And then sort of secondarily to this, we have sort of corresponding to the two properties I mentioned on the last slide, is that we want to minimize the number of type annotations. If we have special things that go in there just so we can type check it, then all the optimizations are going to have to deal with this. And optimizations are probably, they're already complicated enough. We want to avoid this if possible. And secondly, as I said, we want to match the abstraction level of the program, of the intermediate representation we're compiling. We want to think about things in terms of objects, vtables, and methods. And this will make it easier for the compiler writer to deal with. So now I'll start to describe the lightweight type system for objects that we developed that satisfies these requirements, these three requirements that I outlined before. So as I said, the most important factor is soundness. Explicit so the main trickiness here is, compared to the source level, is explicit self-application. So, at the bytecode level, we pass in arguments, but the self argument is automatically passed in by the runtime. If you're interpreting the bytecode, it's automatically done as part of the interpreter. But obviously, in the assembly level, the objects, the CPU is not going to do this for us. So we have to make this explicit. And so for reasons which I'll describe briefly in the next slide, for soundness, we have to make sure that, if we pass in an object, if we take a method from an object, that the self argument is the same as the object we took it from. And if we don't do that, then there can be safety and thus security problems. So how do we describe, so what types are we using? So as I said, we want to match the level of abstraction of the program we're dealing with. So first we have object types. So first there are types like, just class constants like object or vector. And here it just says, this is of a member of that class or some subclass of that. And then secondly, which will allow us, we need more precise types. So we use class of X. And so this means that this object has the exact same dynamic class as the object X. So, right. So this is, if two things have type C, at runtime they may not have the same type. But here, if two things both have type class of X, then we know that at runtime they will always have the exact same dynamic class. And then, so once we have that, it's straightforward to add in virtual method table types. So this just says the virtual method. The first thing is just the virtual method type. This is the virtual method table of the class C. Or we can say, and this is what we use more commonly, is something is the virtual method table of the object X. So it's whatever the dynamic class of X is. We're taking the V table from it. And finally, we have method types. And so on the left side of the arrow, we list the arguments, and then on the right side of the arrow, we give the return type. And so here we have, the first argument is the self pointer. So we know that this method has been taken from the object X, and so we're only allowed to pass in X, or something that's going to be a copy of X. So now I'll give an example of this. So here's an untyped example. So if we assume class C has some method M, and M takes an argument of type D. So first, in the first line, we take out the virtual method table, which contains all of our methods, and put it in Y. And then we take the method M out of Y, and each of these instructions corresponds to a single machine instruction. So first we take out the V table from the object A, and then we take out the method from the V table, and then now we actually call the method in the last line, and we've explicitly passed in the self argument A. And we have to make sure that B is not passed in instead of A. And the reason for this is we only know that A and B are bounded by C. So if A is some class that has a field that B does not, and we pass in B, then Z may try to use that field that doesn't exist in B, and that can cause a crash or a security hole. So that's kind of our main thing. We want to make sure that the first argument is really A. Okay, so now what we do is here are our types, and so these are the types that I described previously. So for the first line, when we take the V table out of A, we know that Y is the virtual method table of whatever the class of A is. And then, so the method M takes one argument of type D and returns an object. So now we know that if we extract the method M, we don't know exactly what Z will be, but we do know that the first argument will be whatever the class of A is, which is our self pointer, and the second argument is of type D. And then now, in the final line, we can apply this. And A has its own dynamic class, obviously, and B does not necessarily. So therefore, we cannot actually substitute B for A. And thus, we have avoided the source of unsoundness. And so if you notice here, these types that we have on the left side here are pretty easy to reconstruct given the right side. If we know A is an object, then we can always tell that it's, the type must be the virtual method table of that class. And if we know about the classes and their definitions, we can tell what the type of, a method taken out from a V table is. So really, we can reduce these. We can eliminate these type annotations and just reconstruct the local variable types during type checking. And so if you notice now, our method body in the type setting, in the typable version of the method is exactly the same as in the untyped version. We haven't added any packs or unpacks, just sort of we haven't added any instructions that exist, solely to type check it. They wouldn't have any runtime effect, but The compiler can manipulate the method body just as if there were no types at all. So now we have a sound type system for objects, and there's a TR with the formal system and a soundness proof. And this is at the machine level. All of these instructions correspond to single machine instructions. And there are no annotations in method bodies. And so we've satisfied our 3 requirements for our system here. So that's nice, but it's not perfect. So the main problem is it's not very expressive. So one thing is how do we reason about optimizations? First of all, there's the problem that we don't have arrays and null tests, but that can probably be added in, orthogonally. But what if we want guarded devirtualization, and we want to reason about, we want to perform more complex reasoning about type tests? Well, we can't really do that here, and that may complicate the system some. But I would argue that by keeping the simple system, so the basic system is very simple, and so if we add on top of it more complex things, the system overall should still end up being simpler. So the second problem is, well, how do we reason about the runtime? So there's different boxes. So we still have, in the diagram I showed, we're still trusting the runtime, and we'd like to avoid that if possible. So Chen and Tarditi have a similar type system to mine, which is more expressive, and it's expressive enough to reason about various standard implementations of a downcast, so which is very nice. So they don't have to trust the implementation of a downcast, and they still have a lightweight type system. They're reasoning about things as objects, and there's not like a huge amount of extra type information, though there is more than ours, but it's still not a lot. So, but I think there's a limit to this approach. So what if we want to show that the garbage collector is type safe? This just extending the type system starts to have some problems with that approach. So we take a different approach. Okay, so what we're trying to do here is, so we've already taken the compiler outside of the trusted system by using typed compilation. Now we want a more expressive way to reason about code than our simple type system allows us. And if we can do this, if we can come up with a system for reasoning about code that can let us check the garbage collector and downcast and stuff like that, then we now have now we're trusting very little. We have some sort of proof checker, which has to know kind of how the machine behaves, and then we trust the CPU. And so now we're trusting a much smaller piece of code. And if we can do that, then our system will probably be more reliable. So how do we do this? Well, you could probably come up with some sort of intermediate stage of expressiveness here, but we just sort of go all out and developed a Hoare logic for reasoning about objects at the machine level. So so we don't just extend the type system for downcast implementation, because if you want to. Because then, what if we want to talk about the garbage collector? Well, you can probably, there are approaches to reasoning about garbage collector with types, but it starts getting messier. And we don't want to pollute the type system that the compiler is using. Because the garbage collector and the compiler really have different views of things. And the compiler should be able to have its nice, simple view of things and not worry about, some kind of weird type thing we need to reason about, the loop invariant of a, Cheney-style garbage collector. So we give up on types, and we just go straight to Hoare logic, and it's very expressive. And so there's a question of how do you, mesh these two worlds together? Well, so the thing is, the Hoare logic is expressive enough that we can reason about types within the logic, and thus we can, after the compiler spits out the typed version, we can automatically convert it into some kind of Hoare logic thing, which we can mesh with the runtime. So how do we do that? Well, basically, we turn our typing judgments into propositions. So, we say if there's an object of type C at address H, if H, if H has the vtable of C, and then there's all the fields are there and they have the right types. And so now we've taken what would be a typing judgment in our simple type system and turned it into a proposition on the heap in the HOR logic. And so now we've laid out all the details of the objects are laid bare, and this allows very flexible reasoning. For instance, you could have some function that adds 8 to all of the fields of an object, and then subtracts 8, and then you could still reason that that if you have a well-typed object at the beginning, that you have one at the end. So you can do all sorts of things, and there has been work on reasoning about like a chain of garbage collector in HOR logic. So we know that we have enough expressiveness to do what we want to do. And so as part of this, I've developed a sort of embedding of objects into HOR logic, and I verified the implementation of a dynamic type check using the standard approach of walking up the class hierarchy and comparing at each step. And another thing this might be useful for would be as a target for something like spec sharp. So if you have more complex invariants in your user code, then it might be nice to be able to translate these down to the machine level and still reason about how these more complex things fit together. But that's something I haven't thought a whole lot about. So what is the future work here? So we have this simple object-oriented type system, and then we have a HOR logic type system, and they're pretty close, but we haven't quite fit them together yet, and there are some slight differences. And so we need to close that gap in order to really be able to construct this full system. And also, the object-oriented type system we have isn't really realistic enough to support all sorts of advanced optimizations we want. So we need to make it more expressive. And also, right now, we just focus on the core, sort of the core thing of dynamic dispatch and field access. And there's more. There's interfaces and arrays and null checks, but that probably shouldn't affect things too heavily. And yeah, so I've done some work on extending a similar type system like this to work in a real compiler that's at Intel. So it does seem within it does seem to be doable. And also we need to verify the type safety of a garbage collector. And then we'll have kind of this entire system that we can put together where all we trust is this proof checker and and sort of the CPU. And something else that might be interesting to look at, as I mentioned, sort of type compilation of spec sharp. And what does that mean? Because once you have more complex invariants, things get kind of funny. Reasoning and relating bytecode to the source code level. So in conclusion, less trust is more reliable. We want to trust as little as possible. Right. So then I've described, at least loosely, a sound typing system for low-level objects, and we do not need annotations or type machinery in our method body with our type system, though it does currently lack some expressiveness that we'd like. And so our approach is to use the type system for the user side, sort of the bytecode kind of side, and then HOR logic to reason about the runtime services we need, and then and also to reason about the combined program. And this gives us the strengths of both approaches. The garbage collector the compiler doesn't have to worry about all the some sort of really complex system, because it only really needs a simple view of things. But at the same time, the garbage collector, which needs more complex view of objects, is able to do that, and they can all coexist in the same system and have their own level of abstraction. So this kind of gives us the strengths of both approaches. So are there any questions? Yeah.
You were talking about object-oriented HOR logic. It was built by you and your colleagues, or you take some object-oriented HOR logic from somewhere?
Basically what we do is we take just kind of a general kind of core logic for reasoning about machine code was developed by people in my group and sort of implement objects within that.
I ask because I read some paper from Abadi and Laino where they describe the Horler logic for object calculus. Did you read it?
Yeah, I've looked at some of that stuff. So.
And what's the connection between your kind of object-oriented logic and this kind of, because this is logic for object-oriented calculus. I mean, there are really a lot of similar things.
Yeah, I mean that's certainly something I need to look at is these other kinds of expressive things for reasoning about objects. Right now we sort of embed the objects within a more general system, which allows us to interoperate different kinds of codes. And I mean, I think a lot of I'm not sure about this particular case, but I mean a lot of the Hor logic stuff I've looked at that includes objects is sort of they kind of include them as a first-class construct, and don't whereas I'm sort of synthesizing it out of existing structures. Yeah.
I may have missed something, but it seems to me that your mechanism is able to mechanically check, for example, that you don't apply a method which comes from a particular V table to this. It doesn't correspond to the same one, but at what stage are you able to verify that whichever piece of software constructed the V table has stuck the right methods in?
So we have to. Yeah, so there's kind of there's the checking where we use the code, and then separately we have to check for each class that the implementation of all the methods is correct. And that's very similar to what you would do at the bytecode level, just kind of making sure that you have the self argument that's the expected type and so forth. So that's all. That part of it is kind of what you would imagine in just.
So is that separately, or are you dealing with that with some variant of Hor logic as well?
Yeah, well, I mean that's just a type judgment. That's kind of a separate thing. But yeah, so it's just a standard kind of typing judgment. So I mean, it's exactly like what you would imagine in C# or something, like how you would check the method that all the methods are right, and then somehow you need to reason that
Well, if you're talking about a bytecode verifier doesn't check that the construction of V table is correct because it doesn't have that abstraction.
Yeah.
So there's extra work. And I realise you've only described a subset of what you've done. You're talking about application there. A bytecode verifier can check type safety of the intermediate form, but there's this piece in the middle, which is the actual construction of the physical layout of the objects. So are you dealing with that as well?
Yeah, so right now in the sort of high-level type system, I treat V-tables kind of abstractly. I just say, well, this value is a V-table from this class. And so I don't actually reason about the makeup of the V-table. So it's very high level. In the Hor logic system, we do actually check that all the V-tables have the right types, and that it's compatible with its parent class and all that other stuff. So, any other questions? Yep.
The examples of things that you want to reject were ad hoc, but I didn't see the exact list of what you can avoid. I mean, did I miss something? What exactly are the violations, or the class of violations that the type system avoids?
Yeah, I mean, basically, we just want to make sure that we have, type safety. So I mean, it's basically like we extract a field from an object, it has that field. If we take a method out of a V-table, it has that method.
So is there a precise specification of what you prove, basically, what you guarantee?
Yeah, so I've proved, preservation and progress. So, it's basically just that, the system won't, won't get in a stuck state, where it can't get a field out or a method. So it'll keep running. The program will keep running, and it won't abort, except in the case of if a typecast fails.
What about null pointers? Do you deal with these at all?
What do you mean?
Null pointers, no references.
Oh, no, I don't have that in here. But yeah, there is a lot of existing work on that. So I don't know. I think that should fit in relatively smoothly with the rest of it. I don't know. Yep.
You said you're using horse logic, yes? Do you mean horse triples like PSQ, yes?
Yeah, it's slightly different than that, but yeah, it's basically like that.
But so it's known that horse logic is incomplete. It doesn't describe complete enough. So procedures with procedural parameters and recursive procedures. This theoretical fact was proven in late 1970s. Does it prevent from your work, or it's okay?
Yeah, no. Some people in my research group have come up with some variants of. It's not quite the same, but it still allows you to reason about function pointers in a limited sense. So we can reason about the function pointers that we need in objects using this sort of other system.